Hello everyone and welcome to Factoring and Applications lesson number 5. So today we're looking at factoring some, they look kind of funny, some funny looking polynomials. They're actually not super scary looking because it's just a big version of difference of squares. So if you know how to do difference of squares, you're going to know how to do this just fine. So it says here, if we look at the expanded form of ax minus by multiplied by ax plus by, you can see that these are conjugates. So what's going to happen is we are going to get the first terms and the last terms, right? We know when we do conjugates, we only have to do the f and the l in our FOIL. So that's going to be ax times ax is going to be a squared x squared. And negative by multiplied by positive by is going to be negative b squared y squared. So the factored form of this, and so in this general form, they're saying that a and b are constants and y and x are variables. I mean, it could be either or, but I think that's what they're trying to get at here. So you could say that the factored form of a squared x squared minus b squared y squared is going to be what we just started with in the top. Ax minus by and multiplied by ax plus by. So it's basically what they're trying to get at is it won't let me scroll. Hang on. Something's freaking out here. Oh, I see what happened. Oh no. Let's see if I can control Z this back. There we go. Okay. There we go. Haha. Can't fool me. So basically we're looking at a difference of perfect squares in these problems. We know 9's a perfect square, x squared is a perfect square, so that whole term is a perfect square. We know 16's a perfect square and y squared is a perfect square. And it's a difference, right? That subtraction sign says that it's a difference of perfect squares or a difference of squares. So we know that when we write these factors down, one's going to be an addition, one's going to be a subtraction. So what two things do we multiply together to get 9x squared? Well, it's going to be 3x times 3x. So we'll put a 3x here, we'll put a 3x there. And then what two values do we multiply together to get 16y squared? Well, it's 4y multiplied by 4y. So we'll go 4y and 4y. And that's it. The next one, we have 3x to the power of 3 multiplied by y minus 27xy to the power of 3. So we can see here that we don't have perfect squares. 3 is not a perfect square. X to the power of 3 is not a perfect square. Y is neither. 27x, and so none of these terms are a perfect square. But you should always, and I didn't do this in the first one, and I should have, always check to see if you can factor something out. In this case, we can actually factor out 3, and we can factor out an x, and we can factor out a y. So what we're left with in the first term is just x squared, right? 3 divided by 3 cancels. X cubed over x is x squared, and y over y cancels. And 27 divided by 3 is 9. The x is gone, and we're left with y squared. So if you look at this binomial here, you can see x squared is a perfect square, 9y squared is a perfect square, and it's subtraction. So we keep our term out front, 3xy, but we can split that binomial into two factors here, where x squared is x times x, 9y squared is 3y times 3y. One's a plus, one's a minus, and that's our answer right there. And the last one, 144 is a perfect square, 4 is a perfect square, but what you can do is you should always check to see if you can factor something out. And in this case, you can factor a 4 out. And 4 times 36 is 144, or 144 divided by 4 is 36. So now we have 36p squared q squared minus r squared. It didn't change any of my perfect squares. 36 is a perfect square, p squared is a perfect square, q squared is a perfect square, and r squared is a perfect square. So now what you can do is split that this whole term up here into its two factors. So 36p squared q squared comes from multiplying 6pq by 6pq. R squared comes from multiplying r by r. One's a positive, one's a negative. And there's our two factors. And that's completely factored out. Had you not factored this 4 out first, you would have ended up with two factors that weren't in simplest form, and you would have to factor those out, factor those as well, and you would have ended up with that 4. I'm not going to do this word problem. I actually think it would be a fun one to do in class as a group, so I'm going to make a note of that. It's a good challenge question, a little bit of application here. But we are going to move into looking at larger terms or more complicated ones, but it's all the kind of the same process. So we know anything with an even exponent is going to be a perfect square, because to get k to the power 4, we can do k squared times k squared. So now we can just split this into, well, it's k to the power 4 is a perfect square, 1's a perfect square, and we have a subtraction. So now we can say k squared plus 1, k squared minus 1. But wait, we're not done. So you have to be careful. You have to ask yourself, is this in simplest form? And a lot of times when we've got these to the power of 4 and 1s, you're going to notice that we actually get another difference of perfect squares. So we're going to leave the first one. It's not a difference, it's an addition. We can't do this. So the first one stays the same. But the second one, that was a bad bracket. Hang on, let me erase that. The second one can be split. To get to k squared, we can go k times k. To get to 1 is 1 times 1 plus 1 minus 1. So there is the answer right there. Let's do, which one should, let's do 1 and we'll leave the other. Let's do the C. We'll skip B. We'll do that one in class maybe. So in this one, 2 is not a perfect square and neither is 162. And we have p to the power of 5 and p to the power of 1. So we're probably going to want to try to factor that out if we can. The q and the t are fine. We can't factor them anyways because only one term has a q and one term has the t. So let's factor out a 2p and see what happens. So if that's the case, we end up with p to the power of 4, q to the power of 4, minus 162 divided by 2 is 81, which is great because 81 is a perfect square. P is gone, so we have 81t to the power of 4. So now we have to ask ourselves, is this term a perfect square? And you can see p to the power of 4 is, q to the power of 4 is, 81 is, and t to the power of 4 is. So we can rewrite that as p squared q squared multiplied by p squared q squared to get each of those to the power of 4. And then to get 81t to the power of 4, we're going to do 9t squared minus 9t squared. Now ask yourself, is this in simplest form? Can I factor anything out? Can't really factor anything else out, but you can see that this one is a perfect square because p squared is a perfect square, q squared is a perfect square, 9 is a perfect square, and t squared is a perfect square. And it's a subtraction. So now we're going to have 2p, and then we're going to have p squared q squared plus 9t squared. That's all the same as above, but now we're going to split this one into two factors. So p squared q squared comes from multiplying pq together, and 9t squared is 3t and 3t. This one's a plus, this one's a minus. Ask yourself, is this as far as we can go? And it looks like it is. So there we go. Bit of a complicated one, but it's the same skill over and over again. It's just recognizing, right, that perfect square, or difference of perfect squares, difference of perfect squares. So you can keep taking it further. You can even do this with binomials. So in this case, we have a squared is a perfect square, subtract b minus c squared is a perfect square because it's all squared. Right? We know if I were to rewrite b minus c squared. A would be b minus c multiplied by b minus c. So now we can do this kind of the same way as we would do everything else, right? So to get a squared is a times a, one's a positive, one's a negative. And then to get b minus c squared is going to be b minus c, b minus c. And now the only other thing you want to do is make sure that they're in simplest form. So this one here can't really change. It's just going to be a plus b minus c. But this one here, we have a negative sign out front of this term right here. So what this is going to do is it's going to change that negative sign right there in front of the negative c. So now this becomes a minus b plus c. And that's because we're subtracting, here, let me get a highlighter, we're subtracting a negative right there. So when you subtract a negative, you get a positive. And that's your final answer. You don't know what A, B, or C is. One more example, and then we're done, I believe. Yeah, we can do that second one, or the second one, or one on the next page to in class. It's a good challenge one for you. So 2x minus y, that whole thing is squared, so it's a perfect square, minus x plus y squared, so that's obviously another perfect square. So we're going to have nested brackets here, 2x minus y, 2x minus y, and then one will be an addition, one will be a subtraction, and then to get x plus y squared, it's going to be x plus y, x plus y. And so now we want to expand and combine. So what we're going to do is say, okay, well, this is going to be 2x minus y plus x plus y. And this one's going to become 2x minus y minus x minus y. That minus is on the x and the y. Right? It's like you're factoring in a negative 1 if you want to think of it that way. So now we got to combine our like terms. We have 2x plus x. So now we have 3x. And we have negative y plus y. So that just cancels out. In the next bracket, we have 2x minus x. So we just have x. And we have negative y minus y. So negative 2y. So you can write it like that. Or you don't have to put that 3x in brackets. It's just kind of out there. X minus 2y. There you go. Cool. That is looking at difference of perfect squares, but a little bit harder, and looking at some of them with binomials as well, or looking at difference of perfect squares ending up in another difference of perfect squares, so you have to do it twice. And that's pretty much it. So thanks for watching. Don't forget to like and subscribe.